Alright guys, so welcome to the first episode of the Bayesian Statistics under 10 slides. So in this video, I'm going to talk about Bayesian linear regression, not your standard average, normal day, user day linear regression, but the Bayesian one. Right? We're going to see how Bayesian linear regression, how Bayesian sees the linear regression problem and how Bayesian solves it. So, if you are not familiar with Bayesian statistics at all, I would recommend you to read the book written by Peter D. Hoff, and his title is First Course into Bayesian Statistics, Bayesian Statistical Methods, I guess. I'm going to post the link down in the below, in the description section, right? So you can click the link and you can easily see how the book is, made. So, I think so. There are several introductory materials on Bayesian statistics, and in my opinion, I think the first course into Bayesian things I'm gonna call FCB. FCB textbook is by far the best one, hands down, I guess, because especially if your major is statistics and you are a bit familiar with the some of the concepts like mathematical statistics, and you have done some little bit of calculus, some linear algebra, then this book FCP really delivers you the essence and the core of the Bayesian statistics. So of course there is a book called Bayesian Data Analysis by Andrew Gellman, the classic Bible of Bayesian statistics. But that book is originally written for graduate school students. So if you're an undergraduate, and you are not, if you haven't finished your 8 semesters of coursework in statistics, then you might find it difficult to read the Gellman BDA book. So I would recommend you to read the FCB by Hoff, right? So in this video, I'm going to assume that you are all a bit familiar with the conjugate prior concepts like Bayes rule and conditional distribution, etc. Okay, so and also I would also assume that you have already someday in the past encountered the linear regression setting, right? So let's get started. So if you review what the linear regression was, that the linear regression was a model for regression. So in the regression problem, we have a column vector that is called y, which is our target, or in statistical jargon, our dependent variable, right? And along with that y vector, we have the matrix X matrix, which is called design matrix. So we have a variable from 1 to p, right? x1, xp as a column, and when we stack that against side by side, and we have a matrix that is called a design matrix, n by p matrix, right? So let's say our problem at hand is to predict or set up a model that explains the behavior of y given a specific row of x, right? And there are many ways to do that. There are many models to solve that regression problem, but the simplest one to understand and to execute would be the linear regression model. So the essence of the linear regression model is the conditional mean. It's the linear conditional mean right here, right? So the conditional mean of yi, the ith observation of y, given the ith row of the design matrix, is linear in the regression in the linear regression setting. So it doesn't have to be linear, right? And for any conditional mean, there's no rule that says conditional mean has to be linear. But the core of the linear regression model is that conditional mean is linear, right? And also, if you add one more assumption that assumes that the error right here, this error follows a normal distribution like this one, then we have a normal linear regression, which can be summarized with this expression: yi follows a normal distribution whose mean is conditional on xi, right? And its variance is homoscedastic, right? Its variance is equal across all possible range of x's, right? So if you add one more assumption that is called IID assumption, which means that conditional on xi, all the all the dependent variable y1 to yn are all, IID samples, right? So if you add all these assumptions, then you get a multivariate normal likelihood. And if you write this full density, then we have a density right here, right? So the y right here is the column of y. So this multivariate normal specifies the entire distribution of the y column vector, and we set the mean of this column vector to be x beta, right? So x here is a design matrix m by p, and beta is a column vector of coefficients, right? So it has dimension p by 1, right? So now that we have a probability density, if you interpret this probability density in terms of the parameter like beta or sigma squared, then we have a likelihood. We have a likelihood, right? And what he have done, or he have learned in school, is a frequentist linear regression, I guess. And in the frequentist scheme, the frequentist strategy for pinpointing an optimal beta is to solve the optimization problem, right? It's the optimization problem of maximizing this likelihood by using the beta, and the single beta that maximizes this likelihood, it was called the MLE, estimate of beta. And especially in linear regression setting, the MLE estimate and the ordinary least squares estimates were equivalent, right? Because maximizing this density right here, which is equivalent to minimizing the term inside the minus exponential term, which is the density, which is the error, some might call. So anyway, in the frequent linear regression, the optimal beta estimate was MLE, yeah, right? And the strategy for getting that is to take a derivative of this likelihood with respect to beta. So for that purpose, we can use the vector derivative rule, or we can use a projection theorem, right? So result from the projection theorem right here, and if you're familiar with it, then it's good for you. If you haven't seen this kind of equations before, this theorem before, then it's safe to just skip it, right? It doesn't matter. What matters is that once the frequency inference, once you get the specific value of this beta estimate, then you go further to get the sampling distribution of this estimator, right? So in this case, the estimator here was the linear combination of y, right, which follows a normal distribution. So this beta hat also follows a normal distribution by the linearity of normal random variables. And if you do after some bit of algebra, you can see that beta hat follows a normal distribution, where its mean is the population beta itself, and variance is the term right here, sigma squared x transpose x inverse. So with this sampling distribution, we have done interval estimation, right? We acquired the confidence interval, like 95% confidence interval, of which the meaning is dubious, I guess. No, I believe so. I don't really like the term confidence interval. It is not a probability interval, right? I'm not going to delve deeper into this concept, but confidence interval, I think it's one of two things that people get wrong about frequency statistics, and in the second of them is hypothesis test, right? Anyway, the sampling distribution, frequentists have done interval estimation and hypothesis test, and the core of the frequentist inference was to first solve the optimization problem and get an MLE, right? And the second is to get a sampling distribution of MLE, right? With which they would do all such things like interval estimation or hypothesis test, or etc. Their favorite things, right? So that's it for the review of the frequentist linear regression. Now let's get to the point. Let's see how Bayesian tackles the same problem, the same linear regression problem. But before that, I'm gonna have to go over some preliminary, concepts about Bayesian statistics. I mean, it's more like tricks here, right? Because what we are going to do, we're going to derive a posterior for each of the parameter, and in order and to make you, go smoothly over the derivation of the expressions, it might be better for you to be familiar with these two tricks. First of all is the matching trick for normal family, right? What it means like this. So let's say we have a y random vector, has a multivariate normal, follows a multivariate normal, which means mu, and a covariance matrix is sigma, right? If you write the density, and let's say if you disregard all the the constant part in the inverse of determinant part right here, then you can say that the density right here is proportional to the exponential term right here. And if you disentangle this parenthesis, then you get some terms like this. Of course, you have something else right here, but we have just disregarded that with this proportional to symbol. The key point is that if you see a random vector, if you spot that a random vector y has a density that is proportional to this exponential term, and inside the exponential term you see a quadratic form of y, right? And also this y transpose b, then we can say, right, comparing these two spots right here, you can say that the expectation of this y would be, the variance of this y would be a inverse of a, and the expectation of this random vector would be inverse of a times b. Alright, this is just matching, SITch, right? There's no such voodoo special magic right here, but this trick is very important. It comes in very handy when you go through some hairy maths that we're gonna cover later in parts. And second tip or trick or second point I want to address here is the inverse gamma PDF. So we all know what gamma PDF is, right? If that's so, inverse gamma PDF is nothing special. You just do a change of variable and multiply Jacobian, and you can easily get this density. But the important part right here is not the constant part. Yeah, you can just disregard this constant part and focus on these two terms, right? So the point is this, right? I made a mistake right here. There should be no zero here. No, I'm gonna fix that right after I finish the recording. Anyway, the key point here is that while you were doing while you were deriving the posterior, if you spot these two, right? If your goal is to get a posterior of the sigma squared, and then inside these expressions, the hairy expressions, if you spot this term, the inverse of sigma squared term, and also the inverse of minus 2 sigma squared over nu 0 sigma 0 squared inside the exponential term, then you can reasonably guess that this posterior of sigma squared would belong to the inverse gamma PDF family, right? So that's it for the two tricks for the deriving the conjugate posterior. And now let's get to the point. So I'm going to discuss how Bayesian treat the linear regression problem. So I may have emphasized this for several times in my Korean classes, but for English listeners, this would be the first time. But in Bayesian inference, the two pillars of the Bayesian inference is first of all the prior, and the second pillar is the likelihood, right? The likelihood that Bayesian address is exactly the same thing that the frequentist address, but whereas frequentists treat the likelihood as something to be maximized, something to be optimized, Bayesian use Bayes' rule. Bayesian use Bayes' rule to get a posterior of the parameter in the likelihood, which means that Bayesian, first of all, before saying the likelihood, Bayesian imbue a prior over that parameter in the likelihood. So if you put prior and the likelihood together, then you get a full probability model like this, right? So in general case, right, the likelihood will be something like this one, right? X is a data and theta is a parameter. And frequentist maximizes this likelihood with respect to the theta, and that one single theta is their estimate, and they get their sampling distribution of this estimator. But the Bayesian use Bayes rule, right? I mean, in both frequentist or Bayesian setting, our goal is to get some results, some conclusions about the parameter, right? In Bayesian setting, the Bayesian, they derive the posterior, which is the condition distribution of theta given the data, right? And it goes something like this. Using the all familiar Bayes rule, you can easily see that this posterior is actually proportional to this likelihood and the prior, right? So, and since this part is just a constant, because theta here, the uncertain random variable theta is integrated away, and then what all that is left is x theta, and since x theta is known, this denominator here is known, right? It's a known constant. It doesn't even matter. So what matters is this. It is incorrect to say it does not matter, but I would like to say we can just disregard this constant and just put a proportional to symbol here and say this one, right? So and this and this conditional density and marginal density, it itself constitutes a full probability model, right? So the lesson here is that once you set up a full probability model by setting up a prior, right, and by setting up a prior for a given likelihood, then you automatically get a full probability model. And getting a posterior is just a matter of getting a margin on conditional density from a joint density, right? It's just a matter of simple, mathematical statistics concept. Right? It's just a simple probability calculus. Bayes rule is just simple as that. And in linear regression setting, our parameter was beta and sigma squared, and our likelihood was this one. So, doing Bayesian analysis of linear regression is equivalent to giving a prior on both of these parameters and getting an appropriate posterior, preferably that is conjugate, right? There are actually two ways, right? At least in this textbook, in this first course into Bayesian statistics, the chapter 9 covers the linear regression part, right? And the author introduced the two methods for giving a prior. The first one is to give an independent prior, right? Independent prior for each of beta and sigma squared, right? The second one is to give a dependent prior. That is, you give a marginal prior for sigma squared first, and then conditional on that sigma squared, you give a prior on this beta. Right. So there are pros and cons for each cases. The pros of this setting, this prior, is that these parameters are essentially independent, right? But the cons is that if you give a prior like this in this fashion, it is impossible to get a closed analytic form of a full joint posterior, right? It is impossible to get, to figure out this posterior in a closed form, right? Which means that we don't know this expression, the mathematical expression for this one. But instead, we can get, if you give a prior like this one, we can get a, the full conditional posterior, which is a, posterior of one parameter given the data as well as the other parameter, all the other parameters. So this one we cannot get. But these ones we can get. If we can use Gibbs sampling, because all the full conditional posteriors are available, you can use Gibbs sampling to sample from this posterior, right? I'm gonna go cover that. I'm gonna talk more about this topic later on. Okay. So in the diagram, this is actually called the Bayesian network. The circle here, the uncolored circle here, denotes a random variable, and this This dot here denotes is something that's other than random variable. Xi is a deterministic parameter, and nu 0, sigma 0 squared, and all these things are priors that you gave. Alright. I just drew the picture to visualize what we're doing here. So this semi-conjugate prior has no dependence, between these two things, right? But the dependent prior has a dependence. The beta is dependent on the sigma squared. But the upside of this, dependent prior is that we can get a closed form of this full conditional posterior because it can be factored in this fashion, right? And we're going to talk about, first we're going to talk about the first one, the semi-conjugate posterior, right? So for the semi-conjugate posterior, we have to derive two things, right? The full posterior, full conditional posterior of this beta, and the second thing we have to derive this one, right? So deriving the full conditional posterior are a bit, in my opinion, a bit analogous to deriving the posterior in a single parameter inference, right? For example, in this one, in this case, if you know the conjugate prior and posterior for the multivariate normal density, then you can easily follow up with this equation. So first of all, the posterior is proportional to this likelihood in prior, right? And since this likelihood, which is a normal regression likelihood, which is linear regression likelihood, which is normal, and also this prior for beta is also normal with to beta 0 and sigma 0, we can combine these two densities inside the exponential term and disregard all the constant part, all the unnecessary part, which include the sigma squared or sigma 0, right? And if you if you expand the expressions, then you get this one and this one. And if you remember, this is the point where we use the matching trait, right? So because our interest here is to get a density of beta, we are going to rearrange this term into quadratic form with respect to beta, and the result is this. So inside the beta transpose and beta, we get this one, which is equal to the inverse sigma, the inverse of covariance matrix of this is beta posterior. And in this one, we get this right here. And I'm not going to, read aloud all the symbols and Greek letters. But the end point is this: once you reassemble, this posterior, this proportional posterior into quadratic form, we can easily get a parameters of the posterior, beta posterior. So, and the result is written right here. So, for the intuition, right? I'm gonna give a little intuition about this result. So the inverse of covariance is a precision, right? Just as the inverse of variance is a precision. So if you are familiar with something, if you know some density very well, then your variance will be low, which means that your precision will be very high, and vice versa, right? So in this case, the posterior precision is given as a addition of data precision and prior precision. This is prior precision because we have defined it to be, and this is called data precision because this one is actually the variance of the beta NLE, which was this, right? And you take the inverse of this, and we have a data precision because it is because NLE is the optimum points of the data, and we call that, and this one is the inverse of the MLE. Then we say this the data precision because it is completely purely out of data. And for the the beta n, the mean parameter, this mean parameter is actually a weighted average of the prior mean and a data mean, right? Because since this is the inverse of the precision, right? So you can say that the precision are in the denominator, right? and each of the weight of the data and the weight of the prior are given as a weight, right? And inside here we get data favored value and prior favored value. Oh, excuse me for a second. Sorry for the interruption. So anyway, so the result here is this. We get a full conditional posterior of beta. So if the prior precision is very low, and when you say matrix is high or low, I mean the size of the matrix is high or low, we usually refer to the determinant of the matrix, right? Because the determinant of a matrix is somewhat a magnitude, the signed magnitude of the matrix, right? So if the precision of the prior, if the precision of the prior is very low, then this quantity right here would be really very similar to the MLE, right? You can easily see that. Just like, expand this insert this equation, insert this expression right here, and you can see this very easy, right? And also, if you don't want the bias incurred by this beta zero, because the beta zero is here, right here, will give you a bias, that is that's not related to the data, because this beta zero mean parameter would drag you away from the data favored point. In this sense, we say beta zero introduces some bias. But if it's the case that you have no prior knowledge or prior belief on the the relationship between y and x, then it would be sensible to say that your prior belief on these slopes is that it is all a zero, right? Because you don't know any such things, right? So if that's the case, if you want, and if that's the case, if that's what you want to do, then we can set beta zero to be zero, the actual zero vector, right? And also aside from that, and plus we can set the sigma zero to be proportional to the data variance, right? The variance of the MLE, and with some scale factor g, right? Then this beta posterior would follow this one, which is very similar to the MLE. And if you recall, the MLE followed a distribution like this, right? And if you switch it, right, and in frequent setting, the sampling distribution of the distribution of this sample, this is the function of a sample, right? The estimator is a function of sample. So in frequent setting, this distribution is about the distribution of sample, as opposed to, in this case, we are talking about the distribution, the posterior distribution of this parameter right here, right? But these two, density are pretty much analogous, albeit these have a different meaning. And the scale factor g, the role of this scale factor g is that if you set g to be very, very large, then it would be more, the g plus 1 over g would be more and more like 1, right? And and in that sense, we say higher g means a weaker prior, right? It means that your prior knowledge affects less in the posterior distribution. And in the contrary, if you set g to be 1 or something smaller than that, then your posterior mean for the beta would be very small. Also for the your variance will be also very small, right? So usually we set g to be equal to the n, right? In this sense, that is because if you set g to be n, I'm not sure if I'm saying this correct, but if you set g to be n, then it translates into saying that you give equal importance to your prior as well as the data. I'm not sure if it's right, but please correct me if I'm wrong here. But anyway, we have derived the full conditional posterior for this slope, right? So next one is the sigma squared. But The posterior for the full conditional posterior for sigma squared is very much same with the posterior for sigma for the usual normal likelihood, except that the we have the sum of square of residuals here, right? So this equation is pretty much the same with the standard normal likelihood posterior sigma squared, except that we have this term right here. So the posterior parameters nus n and sigma n squared can be easily determined to be like this, right? So the prior so nu n is the sum of the prior and data sample size, and nu n squared is the sum of the pooled variance, right? Because the variance from the prior, the sum of residuals from the prior and the sum of residuals incurred by the data divided by the nu n, right? So that was easy, and now that we have the full conditional posteriors, we can do a Gibbs sampling. First of all, so the Gibbs sampling persists like in this fashion. So you start with some initial estimate of the sigma 1 or sigma squared or beta 1, usually straight from the data, right? But it doesn't matter what initial estimate you give, as long as you give enough of a burn-in period in the first proportion of the samples, right? And after that, you generate samples of sigma. The second samples of sigma conditional on the data and the beta, right? And also in turn conditional on this sigma squared, you get another sample of beta, and you can proceed this sequence of samplings on and on. And after some initial burn-in period, let's say you discard this part of the sequence because this part have some effect. Is somewhat affected by the initial estimate. Then with the rest of the estimates, the rest of the samples, the rest of the samples are basically effectively these are samples from the posterior, joint posterior. So this is the core idea of the Gibbs sampling. The reason here is that I may cover this more in detail in the next video, but to briefly say, the idea of Gibbs sampling is this. So let's say your goal is to traverse the mountain, right? Mountain, which is the probability density, where you have two parameters, right? If you are aware of the full, being aware of the full, joint, density of theta 1, theta 2 is equivalent to, you are climbing up the mountain or you are hiking the mountain, and you have all the information about the mountain, and you have exact altitude, is that right? Is the altitude what was the word for the above sea level? Was it the altitude? Yeah, I'm just gonna say altitude. You are aware of the exact coordinate of your location, and also as long as the exact altitude of your point, right? But in many cases, you would only be aware. You are only given. Let's say you are only given a some function that's known to be proportional to this to the exact density, right? That means that you do not know the exact altitude of the point that you are standing on, right? That you're stepping on. But you do know whether this point right here is higher or lower than another randomly selected point. And that is the idea of Metropolis-Hastings algorithm. But the Gibbs sampler is this, right? You do not know the exact altitude of the entire mountain, but given a specific point, given a specific line, right, like here, right, like this one, then given a specific value, of the theta 2, then you are given a complete, information about this, the slice of a mountain, right? And the same one goes for this case where you are given a specific value for theta 1, right? You have the full information about this portion of a mountain. So and if you start from somewhere around here, and sample, and sample the value of theta 1 with this information, and also at this specific point you sample from the full conditional probability, then you can safely assume that if you do this kind of zigzag mountain climbing long enough, then you would be you would have traversed enough of the mountain, right? Would have been through pretty much all the significant areas of the mountain, so that you can map the you can draw a map of the entire mountain. You can do a contour plot of the mountain. That is the idea of a Markov chain Monte Carlo method in general, and then this Gibbs sampling is a special case of the MCMC, where you are given the only a conditional posteriors, right? So the Gibbs sample is also easy to implement in codes, and I have a code example right here. And for your information, right, let's run the code my computer. So I have this RStudio ready, up and going, right? So just gonna move myself to the left. So this is the set of packages you need. So everything, you don't really need anything other than some ggplot2 or tidyverse, and if you have that, then you can run this code chunk, right? So the data from this textbook are available at the website of the book, and I just get the URL of the one of the data. So given the data, so once you import the data, you allocate the variable y in design matrix x, right? And before going into the stepping into the Gibbs sampling, there's some prep work to do. First of all, is to get a sufficient statistics and get a initial estimate. The sufficient statistics from the data. So for the g prior, we set the length of y to be g, and for the prior for sigma squared, we set to be 1, and the data standard deviation of the data, right? Yeah, standard residuals of the data, and also from n, and we set n and p value. And instead of an MCM, so like this one, first of all, let's set seed, right? Guys, don't forget to set seed all the time. And we're gonna run the MCM sequence for 10,000 times, right? And beta, the capital letter beta, and sigma 2 is a placeholder where we're going to save our results in these iterations. And for the initial estimate, we also we are going to use the estimate from the data. And now we run the Gibbs sampling, right? For the Gibbs sampling, so the essence of the coding for the Gibbs sampling is the sequential sampling for each parameter. So in this one, in this code, we sample from the sigma squared. We sample sigma squared conditional on the data and given beta. In this one and the next one, we sample beta conditional on the sigma value that were just generated right here. If you run this code, right, which is pretty quick in this case, then we get a result like this one, right? So what you are seeing is the marginal posterior of each of the beta coefficients. This one is the beta 1, beta 2, beta 3, and beta 4. So like I said, it is impossible to do a integration by yourself to get an exact closed form of the marginal posterior. But instead, we using the samples, generated sample from the full posterior, we can draw a marginal histogram to approximate the marginal density of each of the beta coefficients, right? So if your question is whether the beta 2 is above 0 or not, then you can just read the histogram, right? And read how many portions of the data were above 0. And if that is 60%, then you can say the probability of beta 2 above being 0 is approximately 60%. That is Monte Carlo approximation. If you think about this, in frequency setting, when you want to say beta 2 is above 0, then what have you done? you've done a confidence interval, right? And you have calculated the confidence interval, and you have shown that you can show the confidence interval, or the lower bound of confidence interval is above 0. Or you can do a hypothesis test, right? Hypothesis test where your null hypothesis is that beta 2 is less than 0. And you can, and based on the data, you can reject the null hypothesis. But that confidence interval thing in hypothesis testing is all too complex for average people who haven't invested a several semesters in statistics to understand, which means that frequentist inference is basically, it is really hard to communicate the result to people who use data, people who need your statistical inference analysis, right? So in most cases, people have misundertake the confidence interval to be probability interval. They mistook p-value to be a probability of the null hypothesis given the data, which is not. Frequentist inference cannot say such things as probability interval of a parameter or the probability of a hypothesis. That is not possible at all in frequentist inference. Why? Because in frequentist statistics there is no such thing as prior, right? All the complexities that is involved in doing a frequentist statistics, understanding it all comes down to not using a prior. But in Bayesian statistics, because we use a prior, all the results are very easy to understand and very easy to communicate. So that is the point I would like to emphasize many times in the future videos. Okay, so this is why I'm a personal advocate of Bayesian statistics. I don't really like frequentist statistics because the exact reason that I started studying statistics is because I had no clue what a p-value is, what a t-stat or these little stars in the t-stat means, right? And I do not believe in such things. I do not believe that frequentist statistics can give users of the data some useful information, right? Although the results of the frequentist inference and Bayesian inference can be somewhat similar, the fundamental difference lies in how frequentist and Bayesian gives answers to the people who gave you the data to be analyzed in the first place. Alright, enough for that. Let's head on to the next topic, which is the full conjugate posterior. And for that video, I'm gonna pause for a bit and resume after some break.